Okay. Anyways, but I don't know. To be fair though, this lesson isn't that bad conceptually, so it's just, hey, you see this derivative? Cool, do it again. Like that's basically the entire lesson summarized in like 5 seconds. So, yeah. Anyways, now that we have that taken care of, are there any questions on anything? Any pressing homework questions you would like me to ask or answer? Not ask, answer. Okay. Alright, so nothing much in the way of announcements today. Quiz 4 is next Monday at 9 a.m. to Tuesday at 9 a.m. That's your good old 24-hour window, and it covers lessons 11 and 12. Alright. And that's literally it. So, pretty mellow until quiz, or exam 2 rolls around, so yeah, that's it. Cool. So, let's go ahead and start by talking about some good old higher order derivatives. So, recall from the past few lessons we've been looking at. So we have f prime of x, df dx, we get y prime, and then dy dx. So what you'll notice between these 4 expressions is that they're essentially different ways of saying the same thing. So in that, if you have some function y equals fx, then all these are the same thing as saying you're just taking the derivative one time. So take derivative once. And yeah, that's basically it. So from this you might think, okay, well that's good and all, but is it possible to go even further than that? Can we consider the derivative of, the derivative? And the answer is, yes you can. So, if you want to consider the derivative of f prime, then you can do that. And here we denote that as, well, respectively, we have f double prime of x, d squared f over dx squared, y double prime, and then d squared y over dx squared. Okay. And if you're even curious if you want to go even farther, you can do that as well. So can go further with y triple prime, y is the 4th prime, and so on and so forth. So, yeah. So basically, like I said, if you want to do more derivatives, you can. That's basically the premise of today's lesson. So here's what that says. So like we said, we have f prime of x, df dx, y prime, and dy dx. Okay. So, like we said, that's one derivative. But if we were to then differentiate that, differentiate, we then have, all right, well, f double prime of x, d squared f over dx squared, y double prime, and then d squared y over dx squared. So that would be 2 derivatives. Okay, and like I said, bless you. Bless you. So then if you want to go even further than that, like you said, differentiate again. So then in this case, you would end up with, well, as you might have guessed, f triple prime of x, d cubed f over dx cubed, y to y triple prime, or then a d third y over dx to the third. And that will be 3 derivatives. And then from that you get the idea. So if we keep going, then you can say, all right, well, dot, 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 dot. And then if you want to generalize this to the nth derivative, then this would say, all right, well, you would have f of, with this parentheses n here, of x, d to the power of n of f, dx to the n, y parentheses n, and dny over dx to the n. And that would be n derivatives. Okay. And then you can keep going indefinitely provided your function allows you to do so. Okay, so doot, and doot. Okay. So basically the green arrows here just indicate you can keep differentiating as many times as you want, provided your function will let you do that. But the nice thing is that in this class, you usually are allowed to differentiate the function as many times as you want to. So, okay. So any questions on that? All right. So the first example I want to bring up regarding that is example 1. So let's let y equal 10x cubed times the natural log of the square root of 11x. So we're asked to find the second derivative of this. So we say, all right, well, if you want to take the derivative of this, that's fine, but it might help to clean this up a little bit first, or simplify as much as possible before we do that. So what we notice is that we have a natural log inside our expression here. So is there anything we can do to help simplify this at all? Anything we can do? So in this case, since we have a natural log, and we have a square root in here, what do you think we can do with that square root?
We can bring out the 1/2.
Exactly. So we have 10x cubed times 1/2 of times natural log of 11x, which is just the same thing as 5x cubed times natural log of 11x. So that'll help make our lives a little bit easier in this situation. So let's go ahead and use that. So in this case, if you wish to find the second derivative, well, it might help if you find the first derivative. So let's do that. So in this case, what you'll notice is that, well, here we have one function of x times another function of x. So what should that indicate about how we need to find the first derivative? What rule should we apply?
Product rule.
Yep, we got to apply product rule. Good. So if we let f of x equal 5x cubed and g of x equal natural log of 11x, as per the product rule, well, we can get the derivative of f pretty quickly just from an application of the power rule. But then what would the derivative of g equal here? Okay, good. And how'd you get that?
That's like the derivative of the, well, I did 1/11x times the 1.
Exactly, right? So we have 1 over 11x times 11. Because in this case, you have that 1 over 11x is the derivative of the outer function composed with the inner function, and then 11 is just the derivative of the inner function. So here you just have 1 over x. Okay, good. So that is going to be your necessary derivatives for the product rule. So if that's the case, that says, all right, well, product rule will then give you that y prime is then equal to f times g prime. So 5x cubed times 1 over x, then plus g times f prime. So 15x squared times natural log of 11x. So let's see, let's clean this up a bit, shall we? So we have 5x cubed times 1 over x, so one of the factors of x cancel out on top and bottom to get x squared. So ultimately, looks like you're just left with, well, 5x squared plus 15x squared times natural log of 11x. So the good news is that this is not wrong. So if you want to put this in log kappa, it should be able to accept that. But, well, the thing is that we need to find the second derivative of this. So it might help to clean this up a little bit before we move on to the second derivative. So what would you suggest we do to clean this up a little bit? What would be a good idea? So what do these two terms have in common? Yep. So if we factor out 5x squared, well, we can rewrite this as 1 plus 3 times natural log of 11x. So this would be our first derivative. Okay? And as you'll see, the reason why we wrote this first derivative as such is because that'll make our lives a little bit easier when we find the second derivative. Okay? So what we'll notice is that if we want to find the second derivative, well, just differentiate y prime. So in this case, you say, all right, well, we again have one function of x times another function of x. So we again have to apply the product rule. So in this case, we have 5x squared, and then g of x is going to equal 1 plus 3 times natural log of 11x. All right. So then f prime of x, well, again, power rule dictates that's 10x. And then g prime of x would then equal what? Let's give someone else a chance. So, go ahead.
3 over x.
Yep, just 3 over x, right? Because here, the derivative of a constant is 0, so this term goes away. And then we have 3 times the derivative of natural log of 11x, which we established to be 1 over x here. So your derivative of g then becomes 3 divided by x. Okay. So then let's go ahead and apply the product rule to get our second derivative. So y double prime is going to equal f times g prime. So we have 5x squared times 3 over x plus g times f prime. So that's 10x times 1 plus 3 times natural log of 11x. So if we sort of take a page from computing the first derivative and simplify as much as we can, what would y double prime simplify to if we clean this up a bit? Go ahead.
15x.
Just 15x?
For the first portion, the 5x squared.
Oh, yeah, okay. So 15x, sure. Then So then if you distribute the 10x, we get, well, 10x plus 30x, natural log of 11x. So then if we combine some like terms, we then end up with what as our final answer? Now what can we do with these two terms here if we add them up? 25x. And then times natural log of 11x. Good. So that would be your second derivative here. Okay. So any questions on that? All right. So now let's move on to example 2 here. So here we're given some function whose second derivative is 5x squared minus 2 over root x. And we're asked to find the fourth derivative evaluated at x equals 4. Okay. So in this case, well, basically it's the same idea as before in the last example, except now we just have a different function to work with. So before we start differentiating stuff, I might help to rewrite this in a way that's a bit easier to work with regarding derivative computations. So we have 5x squared on the first term, not much we can do there. But then we have 2 times what? Right, x to the negative 1/2. Good. Alright, so that's y double prime. So then we say, alright, well, that would give us that the third derivative is then what? So what would our third derivative be?
10x plus x to the negative 3 halves.
Okay, x to the negative 3 halves. And then as a result, what would the fourth derivative be? Go ahead.
10 minus 3 over 2x to the 5 halves.
Yep, x to the 5 halves. Okay, so that's all good and all. So that will be your fourth derivative. So in this case, we're going to go ahead and rewrite this a little bit differently because of the fact that we have to figure out what our fourth derivative at x equals 4 is. So we have 10 minus 3 over 2 times, well, x to the 5 halves is the same thing as saying, well, we have a 1/2 down here, so that should probably tell us that we have the square root of x to the 5th, using similar reasoning from up here. So, like we said, we got our good old fourth derivative. So, let's go ahead and use that to get our fourth derivative evaluated at x equals 4. So, we have 10 minus 3 over 2 times the square root of 4 to the 5th. So if that's the case, well, what's the square root of 4 to the 5th? You can use a calculator if you need to.
16 and then square root 4? Or would it be 8?
Not quite.
Okay.
32, right. So we have 10 minus 3 over 2 times 32. Okay, so that's the same thing as saying, well, 2 times 32, that's 64. So 3 over 64. So now, in this case, again, this isn't wrong, but if we wish to combine this into one fraction, well, we have to make sure that we can represent 10 as something over 64. So, in this case, what would that something be up here if we want this to be, if we want this fraction to equal 10? Yep, 640, right? Essentially, all you're really doing to 64 is just multiply it by 10 to get the numerator up here. Okay? And now that these two have common denominators, you can just go ahead and combine these to get 637 over 64. And that, ladies and gentlemen, is your final answer for example 2. Okay? Are there any questions on that? So, now that we have the basic concepts down, let's go ahead and see a quick application of this. So, in this case, let's go ahead and look back at our good old position function here. So if we let s of t be the position function in meters at time t in seconds, then as we've already established, if we differentiate the position function, well, then we just get the velocity function v of t. Is velocity function in meters per second? Okay. So that's the first thing that we've already looked at. But now that we have this idea of higher order derivatives, well, we can take the derivative again. So we have, in this case, if we differentiate the velocity function, or if you want to rewrite this in terms of the position function, the second derivative of the position function is what's known as the acceleration function. Is acceleration function and in this case it's in, now in this case you would have meters per second. So in this case you would have meters over seconds squared. Okay. And what's nice about this is that you can replace meters and seconds with the respective units given in the problem. So if you have, in this case, feet, as you'll see in the next example, well, it'll be feet per second squared. So, can also replace meters and seconds with respective units in problem. Okay. So, taking that into account, let's go ahead and apply that reasoning to our third example. So, we're given that the position function in feet of a particle moving on a straight line at time t in seconds is given by s of t equals 20 times t cubed plus 360 times t. So the first part is we have to find the acceleration of the particle at 2 seconds, and then we have to find the acceleration of the particle when its velocity is 620 feet per second. So since we ultimately have to figure out what's going on with acceleration, well, we should probably find the acceleration function first. So in order to do that, let's go ahead and take a look at this. So in this case, if you want to find the acceleration, well, it might help to find the velocity function first. So velocity equals the derivative of position, which equals what? Go ahead.
20t squared plus 360.
Yep, 20t squared plus 360. Good. So then that would tell you that the acceleration function is just the second derivative of position. Well, and that would just be what?
40t.
Yep, 40t. Good. So in that case, we say, all right, well, now that we have the acceleration function, now we can start doing the actual problem. So in this case, we have to find the acceleration of the particle at 2 seconds. So nice thing is that you just let t equal 2 in our acceleration function. So that would just be 40 times 2, which you can pretty quickly see that's just 80. So with part A, nothing much to that. But I will ask you what the units are for part A, though. So what would they be?
Per second squared.
Yep, feet per second squared, right? Because in this case, our position units are in feet and time t is in seconds. Okay? So with part A, nothing much to that in this case. So now let's look at part B. All right? So now we're asked to find the acceleration of the particle when its velocity is 620 feet per second. So if that's the case, that says, all right, well, we should probably figure out when the velocity is 620 feet per second first. So if that's the case, it seems like we need to take our good old velocity function and then do what with it? What we need to do with our velocity? Let's give someone else a chance. So we need to figure out at what time the velocity is 620, right? So what do we need to do with our velocity function?
Set it equal to 620.
Right. So we have to solve v of t equals 620 first. Okay. So if we do that, we have, well, 20t squared plus 360 equals 620. So if we solve for t in this case, what would our value of t equal here as an exact value? I'm gonna take the pencil down. I mean, you have it. So what do you get something for an exact value?
For exact value,
Yeah.
I got the square root of 13.
Okay. Good. So that is good. But just to remind you right quick, while it is correct, remind me why we can't have negative root 13.
Because velocity, the answer for time can't be negative. That's what I meant.
Exactly. Yeah. Okay. So let's go ahead and look at that. So subtract 360 over to the other side to get 20t squared equals 260. So then divide 20 to get t squared equals 13. But then you realize, oh, wait a minute, in problems like these, you can't have time be negative. So t has to be greater than or equal to 0 here. So in this case, you should only end up with t equals the square root of 13 as your time. So in this case, we say, all right, well, now we just have to find the acceleration of the particle at time t equals root 13. So in this case, we just have to do the same thing we did in part A at this point. So now we have a times the square root of 13 is just, well, best we can do as an exact value is 40 over root 13 feet per second squared. And in this case, if we want an exact value, that is the best we can do. Okay? So, any questions on that? Alright. So, what we'll do now is you may have noticed on the next page, that we have some good old try on your own / group work exercises. So basically, you'll have to find the next two derivatives of each of the following three parts. So what I'll say is that if you like to do these on your own, you can, but if you feel comfortable working with a nearby partner, you can do that as well. And I'll say we'll reconvene in about 10-ish minutes at that point. So if you'd like to work with a nearby partner, you can, but if you feel less comfortable doing that, you can work on your own as well. And you can ask me any questions if you would like. So, like I said, we'll reconvene in about 10 minutes, so we'll call that as 9, or in this case, we'll call it 10:11. So, we put the clock up here so you have an idea of time. So we'll reconvene when this clock here hits 10:11. How are we all doing? Good? So-so? Not great? Give you guys a few more minutes. One more minute. Okay. It is now 10:11. Let's go ahead and reconvene. So let's start by taking a look at part A to start off. So this one, if we have to find the next two derivatives of the following, so it might help to start by taking a look at what y triple prime is from given y double prime. So take the derivative of cosine of 6x squared plus 1. And you should end up with what as your derivative? Right. So because of chain rule, we have negative sine of 6x squared plus 1. So that would be the derivative of the outer function composed with the inner function. But then you have to multiply that by the derivative of the inner function to get this whole expression. So that's negative 12x times sine of 6x squared plus 1. So that's the third derivative. So then the fourth derivative is then what? So what do we know? So we have one function of x times another function of x. So if we differentiate this guy, then what would our next derivative be? Yeah, let's talk about this then. So, if we have one function of x times another, well, that means we're going to need to find the derivatives of each of these and then apply a product rule, right? So then, the derivative of negative 12x, well, that's just negative 12 as per power rule. But then what's the derivative of this going to be by similar reasoning as finding the derivative of this?
It'll be cosine 6x squared plus 1 multiplied by 12x, so it'd be 12x cosine of 6x squared plus 1.
Yep. Okay. So then if we apply product rule from this, well, that means we should end up with, well, y to the fourth prime is, so negative 12x times derivative of the second function. So we have negative 12x times 12x cosine of 6x squared plus 1 plus negative 12 times sine of the quadratic, and 12 times sine of 6x squared plus 1. So then as a result, you should have negative 144x squared times cosine of 6x squared plus 1 minus 12 sine of 6x squared plus 1. Okay. So that would be part A. So now let's take a look at part B. So first off, what would be our third derivative if we're given the second derivative is equal to root of 2x cubed plus 5? Go ahead.
I got 3x squared over root 2x cubed plus 5.
Yep. Root 2x cubed plus 5. Okay, so that works. Or if you want, you can also alternatively express this as 3x squared times 2x cubed plus 5 to the negative 1/2 if you prefer that. Okay. So then in this case, I presume you used this and applied quotient rule then?
Yeah.
Okay. So then, what did you get for that? If you use quotient rule?
I got 3x times the quantity of x cubed plus 1 over that equals 2x cubed plus 5, and then times 2x, or 1 over 2x cubed plus 5.
Okay. So then, yeah, so you said, so repeat that. So you have 3x squared times, then what?
Or 3x times x cubed plus 1.
Times x cubed plus 1?
I'm not sure.
Okay, yeah, let's talk about that. Okay. So, what you can do, so what we'll do is, to make things a bit easier, we'll just use this and apply product rule. So, what we'll do here is we'll say, all right, if we apply product rule in the same way we did in this last problem, then let's go ahead and start by finding the derivatives of each of the parts of the function here. So we have 3x squared and then 2x cubed plus 5 to the negative 1/2. Okay? So in this case, let's go ahead and find the respective derivatives of these. So 3x squared, well, application of power rule tells you that's 6x. So then what would the derivative of this be then? Using chain rule.
Oh shit.
That's all good.
Would be 3x squared multiplied by 2x cubed plus 5.
Yeah, 3x squared multiplied by 2x cubed plus 5 to the what power?
To the negative 3 halves.
Negative 3 halves. But then remember, by power rule, you have to multiply this by what? If you're gonna subtract this power here by 1, you can, but you also have to multiply by what?
Multiplied by the negative 1 half.
Bingo. Okay. So then, I'll just do this. So negative 1/2 times all this. Okay. So then that implies that the fourth derivative is then, well, 6x times 2x cubed plus 5 is the negative 1/2. And then, let's see. Oh, wait a second. This, no.
I just
Yeah.
forgot the negative.
Well-
It was supposed to be 6x squared.
Yeah, it's supposed to be 6x squared. Oh, I see what you're, okay, gotcha. That makes a lot more sense. But, okay, yeah. But in any case, yeah. So in this case, you'll have, this will be negative 1/2 times 6, so then you should have negative 3x squared, so that would be minus 9x to the fourth if you multiply it with this. And then 2x cubed plus 5 to the negative 3 halves. Okay? And that would be your fourth derivative. Okay? And then what I'll do for part C is say, okay, since we're about ready to run low on time, I'll just say I'll have them on my webpage and you can look at them there.